In this lecture, we'll discuss integer programming, or IP. A 0-1 variable, also called binary variable, is a decision variable that must equal 0 or 1. Usually, a 0-1 variable corresponds to an activity that either is or is not undertaken. If the 0-1 variable corresponding to the activity equals 1, the activity is undertaken. If it equals 0, the activity is not undertaken. We'll show how many complex problems can be modeled using 0-1 variables and other integer variables. Optimization models in which some or all of the variables must be integers are called integer programming, or IP models. In this lecture, we illustrate many of the modeling techniques that are needed to formulate IP models of complex situations. You should be aware that any optimization software, including Excel solver, typically has a much harder time solving an IP problem than an LP problem. In fact, optimization software is sometimes unable to solve an IP problem, even if the IP problem has an optimal solution. The reason is that these problems are inherently difficult to solve, no matter what software package is used. However, as you will see in this lecture, your ability to model complex problems increases tremendously when you use binary variables. IP models come in many forms. You saw examples in previous lectures where the decision variables are naturally integer valued. For example, when scheduling employees, it is natural to require the numbers of employees to be integers. In examples like this, where you do not want certain decision variables to have fractional values, the problems are basically LP models with integer constraints added at the last minute. In many such examples, if you ignore the integer constraints, optimize with solver, and then run to the nearest integers, the resulting integer solution will probably be close to optimal, although the rounded solution is sometimes not optimal or even feasible. The integer models in previous lectures are not the types of IP models discussed here. If it were simply a matter of adding integer constraints to decision variables, such as the numbers of employees, this lecture won't be necessary. However, many inherently nonlinear problems can be transformed into linear models with the use of binary variables. Most of the models discussed here are of this type. The clever use of binary variables allows us to solve many interesting and difficult problems that LP algorithms are incapable of solving. All the models we analyze in this lecture are, aside from binary or integer decision variables, linear models. As in previous lectures, this means that the objective cell is a sum of products of constants and decision variables. The same goes for both sides of all constraints. The only difference is that some of the decision variables are now constrained to be binary or integer. Although the basic algorithm that solver uses for such models is fundamentally different because of the binary or integer variables, it still helps that the models are linear. They would present even more of a challenge to solver if they were nonlinear. Many problems in the literature are described as mixed integer linear programming, MILP models, which indicates that some of the decision variables are integers and others are not. When Excel solver solves a linear model without integer constraints, it uses a very efficient algorithm, the simplex method. This method examines the corner points of the feasible region and returns the best corner point as the optimal solution. The simplex method is efficient because it typically examines only a very small fraction of the hundreds, thousands, or even millions of possible corner points before determining the best corner point. The main difference between LP and IP models is that LP models allow fractional values such as 0.1 and 3.456 in the decision variable cells, whereas IP models allow only integer values in integer-constrained decision variable cells. In fact, if decision variable cells are constrained to be binary, the only allowable values are 0 and 1. This suggests that IP models should be easier to solve. After all, there are many fewer integer values in a given region than there are continuous values. So searching through the integers should be quicker, especially if their only possible values are 0 and 1. However, IP models are actually much more difficult to solve than LP models. The solution procedure used by solver is called branch and bound. Although we do not go into the details of the algorithms, we discuss briefly what solver is doing. Consider a model with 100 decision variable cells, all constrained to be binary. Because there are only two values for each binary variable, 0 and 1, there are potentially 2 to the power of 100 feasible solutions, although many of these might not satisfy all of the constraints. Unfortunately, 2 to the power of 100 is an extremely large number, so it would take even a very fast computer a long time to check each one of them. So, the naive method of complete enumeration of all possible solutions is usually impractical. However, implicit enumeration is often very practical. This approach examines only a fraction of all 2 to the power of 100 potential solutions, hopefully a very small fraction, and in doing so, it guarantees that solutions not examined have no chance of being optimal. To see how this works, suppose you find a feasible solution with a profit of $500. If you can somehow guarantee that each solution in a particular subset of solutions has profit less than $500, you can ignore this entire subset because it cannot possibly contain the profit maximizing solution. The general idea mentioned earlier is the essence of the branch and bound method used by solver in IP models. The branching part means that the algorithm systematically searches through the set of all feasible integer solutions, creating branches or subsets of solutions. For example, if x1 is a binary variable, one branch might have x1 equals 0 and another branch might have x1 equal 1. Then, if x2 is another binary, two branches might be created of the x1 equals 0 branch, one with x2 equals 0 and one with x2 equal 1. By forming enough branches, all possible integer solutions are eventually examined. The key, however, is the bounding part of the algorithm. Suppose that the objective is to maximize profit. Also, suppose that partway through the solution procedure, the best feasible integer solution so far has a profit of $500. This is called the incumbent solution. Its profit represents a lower bound on the optimal profit. That is, the optimal solution must have a profit of at least $500. This is the easy part of the bounding procedure. The best profit found so far is a lower bound on the optimal profit. The hard part is finding suitable upper bounds. Suppose you are considering the branch where x1 equals 0 and x2 equals 1. If you can somehow show that any solution that has x1 equals 0 and x2 equals 1 can have profit less than the incumbent $500, then you can ignore this entire branch. So the goal is to find an upper bound for each branch that satisfies two conditions. One, it is easy to find in terms of computing time, and two, it is as low as possible. Why should it be as low an upper bound as possible? Suppose the upper bound you find for the x1 equals 0 and x2 equals 1 branch is instead $515. Then, because the incumbent's profit is only $500, this branch might have some potential. That is, it might contain a solution with profit greater than the incumbent. Therefore, you have to pursue it, which costs computer time. The lower the upper bounds you can produce, the quicker you can go through branches and the faster the algorithm will be. The procedures used to find good upper bounds for branches are beyond the level of this discussion. Fortunately, Solver takes care of the details. However, you should now understand some of the messages you will see in the status bar when you run Solver on IP models. For example, try running Solver with an integer optimality setting of 0%, like we did in a couple of examples in the previous lectures. The Solver Options dialog box contains an integer optimality setting which is relevant for integer constraint models. The default setting is 1% in Excel 2013. In earlier versions of Excel, it was also under Solver Options, but in a slightly different dialog box, and it was called Tolerance. To explain the integer optimality setting, you must first define the LP relaxation of an IP model. This is the same model as the IP model, except that all integer constraints are omitted. In particular, cells that are originally constrained to be binary are allowed under the LP relaxation to have any fractional values between 0 and 1, including 0 and 1. The LP relaxation is typically easy to solve using the simplex method, and it provides a bound for the IP model. For example, consider a maximization problem where the optimal solution to the LP relaxation has an optimal objective value of $48,000. Then, the optimal objective for the original integer constraint problem can be no larger than $48,000. So, this value represents an upper bound for the original problem. An integer optimality setting of 1% means that Solver stops as soon as it finds a feasible integer solution to the IP model that is within 1% of the current upper bound. Initially, the optimal objective value of the LP relaxation serves as the upper bound. As Solver proceeds to find solutions that satisfy the integer constraints, it keeps updating the upper bound. The exact details are beyond this discussion. The important point is that when Solver stops, it guarantees an integer solution that is within at least 1% of the optimal integer solution. The implication is that if you use an integer optimality setting of 0%, Solver will, in theory, run until it finds the optimal integer solution. So, why isn't a setting of 0% always used? The reason is that for many IP models, especially large models, it can take Solver a long time to find the optimal solution or guarantee that the best solution found so far is optimal. On the other hand, a solution that is close to optimal, within 1%, say, can often be found quickly. This explains why frontline systems, the developer of solver, chose the default setting of 1%. We use an integer optimality setting of 0% for all the models in this chapter, simply to guarantee an optimal solution. So, if you use the default setting of 1% or 5% in older versions of Excel, you might get a solution that is slightly worse than ours. Until now, the only solver message you have probably seen is the final one that says an optimal solution has been found. When you run solver on some of the difficult problems, however, you might see a few other messages, such as those in the two figures shown here. These are due to solver running a long time and bumping into the limits in the options dialog box we saw on the previous slide. If you see one of these types of messages, you have two options. First, you can change the options in Options dialog box. You would have to make this change before the solver runs. Second, you can simply click on Continue to let solver run longer. We recommend the second option. Actually, if you are tired of waiting and believe the incumbent solution is good enough, you can also click Stop, in which case solver gives you the option of saving the best solution so far.